Hey, recording is rolling. It is Thursday, February 8th. So continuing with Unit 2 Dynamics, we're going to kick off class with some blocks on incline scenarios. You guys got your notebooks out, right? Notebooks out, right? And then I have some AP Classroom Dynamics questions from Unit 2, right? Multiple choice, we'll be going over. On your desk, there should be a review quiz for Unit 2 Dynamics. I think everybody got one of those. Did anybody not get Unit 2 Dynamics quiz on their desk? I think everybody's got one, right? And you guys are writing in your planners that that's due Monday. So you guys got a few days to do that. All right, everybody good there? Good there? All right.
Say what? Say that again?
Okay, so you got a review quiz on your desk?
What we do?
All right.
I don't. I physically do not have it. This one I skipped up on it too.
Okay. It's gonna. All right. All right, so I think we're ready to go. Right, so you guys got that your planners. You guys got notebooks out.
Yeah.
All right, so here's first question for you guys. All right, let's get an incline going. Incline. All right. Yeah. Physics 1. You're gonna get fair share of incline questions. You guys did FRQ yesterday involved in incline. Right. Throw a block on it. Right. Let's say that there's frictionless surface. Frictionless surface. Right. Maybe this is an air hockey table, and that's an air hockey puck. We just tipped up the table to some angle, maybe some angle theta, something like that. The block has some mass m. Right. Yeah. All right. So guys, draw a free body diagram. Draw a free body diagram. FBD for that scenario. Draw the free body diagram. All right, give you guys a minute.
Wait, so what did you say was happening to the block? It's just on the table. That's it.
Yeah, and it's a frictionless surface. Okay, so make sure you write down that detail because that matters too. All right, so frictionless surface, there's zero friction. What does that look like? All right. Some of you guys are getting this. All right, notebook. All right, so I think everybody's got paper now. Everybody's doing this. Everybody's drawing the free body diagram. All right. All right, so I think some of you guys got this. What's one force on this block? How about its weight? Call that mg, or you can do capital F sub g, right? Force due to gravity. I'm doing mass times gravity field, mg, right? What's another force on this block? The normal force. Okay, you guys, normal force. Am I gonna draw that straight up against gravity? No. Right, you guys are right to say no. Right, I'm gonna rotate my ruler a little bit, whatever this angle is. Right, rotate my ruler, same number of degrees. Right, so it's perpendicular now to the surface. Right, and is this normal force going to be a little bit longer, a little bit shorter than the weight? A little bit shorter. Right, right. You can calculate exactly how long it's going to be by doing the weight multiplied by what? Cosine of theta, right? Right. So if that's like 30 degrees, take this weight times cosine of 30 degrees, boom, like that. Right. Are there any other forces on that block? Nope, that's it. That's the entire story right there. Right? Because frictionless surface, right? Oh, could that block be in motion? Yeah, could be, right? Right. And would you know which direction it's sliding? Maybe slide down. That would be okay. Could it be sliding up? Yeah, and it would have the exact same free body diagram, wouldn't it? Right, exact same. Right? So this free body diagram, you don't actually know the direction of motion just by looking at the diagram, right? And whichever way it's moving, or maybe you gave it a push and it went to the top and it's about to turn around, right? All those have the same free body diagram. Okay, so if you give it a push up, do you have to include the pushing force, right? During the push, that'd be true, right? If you're actively pushing it, right? Like yesterday, like you were actively pushing the crate up the incline. Yeah, so you had to include that pushing force.
What if it's like on the?
Okay, yeah, same thing if there's a spring and the spring pushes it. Okay, if it's being pushed.
Oh, like as it's like in the middle of it, not.
Okay, yeah, once it leaves the spring and it's just in motion with some velocity, right? Okay, maybe there's an upward velocity like this, right? Yeah, that spring force is gone. Yeah. Right. Yeah, so yeah, there's maybe kinetic energy, right? It's not a force though, right? Okay, so there you go, right? So just those two forces, right? And if all you see is that like that scenario in that free body diagram, yeah, you don't actually know like if it's in motion and which way it's moving. Okay. I mean, can't say it rests forever though, because frictional surface, but maybe it's turning around possibly. All right. All right. So you guys get there? Get there? All right. Next thing, let's take this scenario. I want you guys to calculate what is the acceleration as a function of this angle theta. Okay, I'm gonna spell that out. Right. So calculate, or maybe here, scratch it. Let's find an expression for it. How about that? Find an expression for the acceleration as a function of theta, right? Maybe there's some other variables that possibly matter too, right? Maybe the mass of the block, maybe the gravity field. Right? But I definitely want to see the angle in your expression. Right? How much is that block accelerating? While you guys are driving that, here's another story you could possibly attach to that. Right? What if instead of being a frictional surface, what if it had little tiny wheels on it? Ooh, that could be one of the first labs you guys did. You guys remember those cars zipping down those inclines? Okay. And those Hot Wheels cars, they were accelerating. Okay. How much? How much are they accelerating? The trip around the room here. Let's see who got the. Anybody got the? You calculate how much the block is accelerating. Those are some ideas that you guys do. What if that angle was 0 degrees and it was just horizontal? There would be zero acceleration. That'd be true. Okay. So whatever answer you come up with, at least has to be consistent with that. Okay. Ooh, what if that angle was 90 degrees? Would that block be in pure free fall? Okay. Okay. All right. Nathan got it. Yeah, Jensen got it. I think Alexander's close. Yeah, Gavin got it. All right, I think some of you guys are getting this. Some of you guys are getting this. So start going through this one. Okay. All right, so I'm gonna modify this free body diagram a little bit. I'm gonna break this weight into components because I want to be thinking in terms of a Cartesian system that's oriented to the surface. So let's go parallel to the surface, perpendicular to the surface, right? So I'm going to think in terms of this rotated Cartesian system, right? My normal force is already aligned to that, so leave that guy alone. But this weight, okay. Say, well, how much is the weight like, pushing into the incline versus how much is it dragging along the incline? Notice right now, I'm holding my ruler parallel to the surface, right? Not parallel to the ground, but parallel to the surface. Right, guess that? Okay. So pretty close, looks like. Okay. And some of you guys may have already done that before, so that you can say, that matches that. Bam. Okay, so same magnitude, right? Okay, so, that angle theta. Is that angle theta? Same angle? Okay. So here's your mg, which one? Sine or cosine? Cosine theta there. Right. That tells you what the magnitude of the normal force is, right? Okay. But ooh, how about this one? How about this one? I think we're going to care about this one for this question. So this is your mg sine theta, right? Okay, so I've effectively replaced the weight in terms of its components. Okay? I see that the mg cosine theta and the normal force just balance out. Right? So the block's not accelerating that way. Okay, that makes sense. But what about this component right here? Right? Does that, in a sense, represent the net force on that block? That's the net force, isn't it? Ooh, you guys see that? Right? So I can say net force equals mass times acceleration. That's Newton's second law of motion. Or maybe you started with the next step anyway. Acceleration is net force on mass. Right? I really prefer to think of Newton's second law of motion in its fraction form like that, right? Well, how much does something accelerate? Well, what's the net force divided by mass? Right? In this case, the net force is mg sine theta. Mg sine theta, right? Okay. So that net force is driving a block with mass m, boom, cancel up, and you got your answer. Okay. Yeah, so walking around, I think at least 5 of you guys got this, and I may have missed some of you guys too. So I missed you, but okay. That's what you're looking for right there. Okay. G sine theta. Right? Let's check those boundary conditions. I threw you guys some hints to say, how to think about it. Right? Suppose so what if this angle theta was 0 degrees? So okay, well the block would just not be accelerating. Right? Ooh, guys, what's sine of 0? 0. So that would zero acceleration. Right. And what is sine of 90 degrees? 1. So that'd be like, acceleration would be the full rate of gravity.
If there was a coefficient of friction, would you multiply it by g times sine theta?
Ooh, what? Okay, so the question is, what if there is friction? We're about to do that. We're about to do if there's friction. Yeah, so hang tight there because we're getting to that. All right. You guys might remember this was one of your thumbnail notes from a few months ago. So this is a long time back. But that's it right there. That's the whole. Oh, thank you. All right. All right. You guys remember that? All right. Boom, boom, boom. All right. So you guys got that in your thumbnail notes from back in the day. All right. You guys ready to add friction to this? Add friction. All right. Let's start pretty basic here. Is let's do a equilibrium scenario. All right. You guys ready for equilibrium? All right. So get another incline going. Yeah, it's be tricky and flip it horizontally on you guys. How about that? You got to be ready to field it both ways, right? Which way's the block side? Let's throw a block on here. Let's say the scenario is the block slides down at constant velocity. Right? Just to make for sure, right? The one that we finished a couple minutes ago, right? Was this a constant velocity scenario? No, definitely not, right? This is constant acceleration. Acceleration means you can't have constant velocity, right? Velocity is changing, right? Right. And again, it could have been velocity either way, right? It could be going up the incline, down the incline, or turning around, right? It's ambiguous as to the direction of motion or how fast it's going. That has nothing to do, right? But the velocity is changing at some constant rate. That's what acceleration is, right? So now I have a new scenario: sliding constant velocity. Guys, if it's sliding at constant velocity, does there have to be friction? Yeah, or at least there has to be like some, maybe some guy tied a rope to it and he's lowering it down or something. Yeah, well, absolutely something like that. Yeah, there's got to be friction, right? So go ahead, draw the free body diagram. Free body diagram. Call it FBD. Free body diagram. All right, walk around the room. Who's getting this? Who's getting this free body diagram? All right. So I think a bunch of you guys were getting this. You guys said, yep, this block has a weight. Now that is straight down, the weight, mg, straight down. Okay. You guys were saying, now there's a normal force. Now it might help to actually, at some point, split the weight into components so that you know how long exactly to draw the normal force. F sub n, normal force. Right, so the weight, right? And then I'm going to break this into components. Right, that angle theta matches that angle theta. Okay, so we got that. Okay. And now if I stop right there, that would not be constant velocity because there'd be a net force and it would be accelerating. That's what we're looking at a couple minutes back. Right, so did you guys say there has to be a friction force? Right, friction force. Right. And is the friction force the same magnitude as this mg sine theta? Right. It has to be, so that the net force on the block is what? 0. Right? You guys see there's 0 net force, right? This normal force balances with this component of the weight. This friction force balances with this component of the weight, right? And that, okay, that would be consistent with constant velocity. Constant velocity, 0 acceleration, 0 net force, right? Right, so next question. Oh, right, and this was a lab you guys did, right? What is the coefficient of kinetic friction? I might call that mu sub k between the block and the surface. Okay. Maybe the block's like made out of aluminum and the surface is made out of steel, or some materials, right? Some material property. Okay. So come up with an expression in terms of variables, kind of like the last one we did. Come up with an expression. Say mu k equals what? So this one's a little trickier. Okay. But I've seen this happen as an FRQ in the past. This has exactly been an FRQ in the past. Right? Like every step is a point. It's a point. Okay, so get as far as you can. And every next step you get is like another point on the AP exam. It's like answering another multiple choice question, correct? Okay. Like a whole treasure chest of points right here. The treasure. All right. Show of hands. How many guys think you have the whole answer? Okay. So, I'm seeing a bunch of guys. Nathan, what you got? Gavin, what you got?
I got, yeah, mg times 10
theta. 10 theta. All right. So everybody's telling me 10 theta. All right. You guys got it. All right. So let's walk through this.
Wait, actually, yeah, I did mg over mg.
There you go. Yeah. Right. So, you got to say here. There might be a little bit different ways to set this up to start this, but I know that this component right here is mg sine theta. I know that the normal force is equivalent to, well, this, which is mg cosine theta. So mg cosine theta, right? So the steps I'm going to do, you might have written this a little bit differently. That's okay. Right? Some version of this, though, right? That this friction force is equivalent to mg sine theta. Okay. I might actually proceed that with something like the sum of the forces in the x direction goes to 0 newtons. Therefore, this minus this is 0. Therefore, that's equivalent to that. Okay. Then that could very well be a point depending on how they score it. Okay. But you guys know something else about friction. Guys, what's another formula for friction? Friction force is equal to what times what? There you go. Coefficient of friction times the normal force. Right? You can say equals as long as it's kinetic, like it's sliding. The static one's a little trickier because it might be an inequality you could build up to something, but yeah, you could definitely say equals if it's kinetic friction. Which was not okay. This question. Ooh, guys, the friction force is mg sine theta, and friction force is also coefficient of friction times this normal force. Hey, can I just take these two and say equal, right? It's that, and it's also that. Hey, right? So okay, we switch a little bit easier to read in color. So therefore, coefficient of kinetic friction times the normal force is equal to mg sine theta. Okay, that okay? Right. But you know what? That normal force said had to be equivalent to mg cosine theta, right? Is that also true? So let's do another substitution. Bam, right there. Coefficient of friction times mg cosine theta equals mg sine theta. Right? Okay. And then, ooh, what cancels out? Both sides? Is the mass of the block and also the gravity field. So if you took this whole system up to the moon, are you going to end up with the exact same result? Yeah, and by that I mean you'd have to tilt to the exact same angle, however many degrees, to get a slide down constant velocities, but it'd be the same on the moon as on Earth. Okay. And last step, I just need to divide both sides by cosine theta. Oh, and what sine divided by cosine? Tangent. Okay. Tan theta. There you go. Right. So this was a lab that you guys did back a few months ago. Right? You guys tilted up your desk until it did slide down at constant velocity. You said you use a protractor to grab that angle. Let's see what mine is. Let's suppose this was actual thing. Let's figure out. So my protractor is reading, what is that, 38 degrees, about 38 degrees. Okay. So I can say, what is tangent of 38 degrees? Tangent of 38 degrees. My calculator's programmed in degrees. Okay, so good. So same 0.78. That's a pretty high coefficient of friction, but yeah, that could be, right? So yeah, so 0.78 it would be for this particular scenario. Okay. Right. And then you know what? You guys do have a poster on this one too. Right. So this is also in your thumbnail notes from back in the day. There you go. There's the full proof. Right? Constant velocity means zero acceleration, means zero net force. Right. And then there you go. And then here's the end result. Okay, it has to be sliding down so that friction opposes above. Okay, you guys go there? All right. How about you guys ready to go a layer trickier? How about this? Let's set up another incline here. Another incline. Let's say at this angle, I'll give you some numbers. How about that? This angle is about 20 degrees, like yesterday. Okay. And let's have the mass of the block. I'm pretty sure the mass is going to cancel out anyway. Okay. Let's call it 1 kilogram. How about that? That could be a trick, right? If you're not given the mass and you think, okay, well, that probably means it's going to cancel out, but maybe that's confusing to do the math, right? Just call it 1 kilogram. And then if it works in general, it should work for any specific value like that, right? Right. And I want to give you one more number, right? That will be important, right? Let's say that the coefficient of friction, coefficient of kinetic friction, is 0.15. Right. So like the friction force is 15% of the normal force. Think of it that way, right? Right. I want to know, what is the acceleration of the block? What is the acceleration of the block down the incline? Right. I guess it would help to know for context too. Let's have this block just sliding down this way, right? With some velocity, right? Which won't be constant because it's accelerating, right? But it is sliding down the incline, right? What's the acceleration? Okay. You guys solve it. I'll solve it. The numbers worked out pretty nice on that one. All right. I think I got the answer. Who thinks they know the answer? What you got, Gavin? Okay, all right, that's what I got too. Right. Let me give you guys a little bit more time. Catch up to Gavin over there, then start going with this. All right, let's start from the solution. Hopefully you guys can stay a couple steps ahead of me throughout this entire process. Right. So, okay, complete this free body diagram as best I can here. I know that this component right here is 10 newtons times sine of 20 degrees. Let's get a numerical value for that. Okay. If you want an even better challenge, maybe you can solve in terms of variables. So that would be a good thing too. Now let's do numbers for this one. Okay. I'm looking at 3.42 newtons. Okay, hold on to that. Okay. I know this component right here is 10 newtons times cosine of 20 degrees. So pop in a cosine, getting 9.40 newtons, right? Which means that the normal force must also be 9.40 newtons. Okay. Now this friction force, I know, is coefficient of friction times the normal force. Right. Right. I gave you coefficient of friction, it's 0.15. And I just found the normal force. So that's gonna sub in right there. Right? So take my normal force, which is that value, right? Multiply by 0.15, right? That tells me exactly what the friction force is, which is 1.41 newtons. Okay? So I'll call this 1.41 newtons, right? So that's the resistive force trying to slow the block down. Right? Notice I drew that that vector kind of small. It's smaller than the component of the weight that's trying to drag the block down in the first place, right? So that there is a net force. You guys see this component is larger than the friction force. Do comparison. Right? Try to do this approximately to scale. And so there's a net force. So what is that net force? Let's find that. Okay. So F net equals, well, in terms of variables, it'd be like mg sine theta trying to accelerate down minus the friction force opposing that, right? That's the setup. Okay? And I have values for each of those. This whole mg sine theta I found to be 3.42 newtons. This friction force, I got 1.41 newtons. Boom, boom. Track those. 342 minus 141. Right. I'm getting 2.01 newtons net force. Right. That's the net force. Right. Sometimes written this way: sum of forces. Right. Net force, sum of forces. That's the same thing. Right. If you sum up all the forces, that's the net force. Okay? Right. Now there is one more step, which is to get acceleration, I have to apply Newton's second law of motion. So the acceleration is the net force divided by the mass. Okay? Well, that's 2.01 newtons acting on a 1 kilogram mass. 1 kilogram, okay? Which gives you 2 meters per second squared. Right? If this was a multiple choice, AP tends to stick to 2 significant digits. You probably see an answer choice like that, right? That could be an FRQ. Right? All right. Hey, guys, good there? It's like a whole process there. How do you get which one? The friction force? Okay. Yeah. So it's kind of crammed up here. Right? How did I solve this friction force? Right. Well, I know that. Let me spell it out here. I know that.
Yeah, get the normal force times the
Exactly. Yeah. Right. So friction force is equal to coefficient of kinetic friction times the normal force. Right. and this normal force was equivalent to mg cosine theta. Right. So I did 0.15 times, and then the mg cosine theta came out to be 9.40 newtons. Right. So that gave me 1.41 newtons. Okay. All right. All right. Everybody still do good. Do good. All right. So, yeah. Any of these review questions we've done so far would be completely fair AP questions on the exam. All right, you guys ready for some of AP's questions? All right, let's switch over and do some AP questions.